Today we are going to start with continuous distributions. Now we are going to study 7 continuous distributions, but the continuous distributions are not limited only up till these 7 distributions, but these are the most widely used continuous distributions. Now we studied uniform distribution as in discrete as well as we are going to study in continuous. Let's start with uniform. Now for discrete uniform distribution, we did not have any notation, but for continuous continuous uniform distribution, we have, let's say our x variable follows uniform u and we have parameters a, b. Now these parameters a and b are nothing but the limits of our values of x. So basically our x is going to be between a and these are the limits of our continuous random variable x. Uniform distribution has same probability distributed equally. That means probability density for a continuous distribution will be equal here. Now always for a discrete distribution we can find probability at a single given point, but for a continuous distribution we cannot find probability at a single given point. So therefore we find probability density. So probability density fx for a uniform distribution with limits a and b is going to be 1 by b minus a. So all we are doing is we are dividing our probability 1 among this much range. B minus a is going to be our range of values. So we can find capital Fx. Capital Fx, that is nothing but probability x is less than a particular value, let's say x. Now when we say probability x is less than a particular value x, the lower limit is always the lowest limit of x. Now the lowest limit of x is here a, so this can also be written as probability a less than x less than small value x. Now if you see, I have not written less than equal to, neither I have included point a here nor I have included point x here, just because at any given point a continuous distribution probability will always be 0. So therefore if I include or if I do not include, it is the same values. It's just preferable not to write equal to signs. Now that is going to be nothing but integration from a to, let's say, a particular value x1. I'll just put x1 here and we'll integrate fx dx. So integration, I have 1 by b minus a dx. Integration is going to give me after putting the limits, we get x1 minus a upon b minus a. Or for a generalized formula, you can write fx is equals to x minus a upon b minus a. So this is nothing but probability less than equal to this particular value a. So if we want to find probability in a continuous distribution, we'll always have to find probability range. This is going to give me range from the lowest value from where this we have a and to this particular value, general value x. We can substitute different values here x and we can find different probabilities using this formula. Now let's find expected value. Now expected value is nothing but integration for all values of x. So for all values we'll have a to b x into fx dx. So we are going to get x square by b minus a into 2. The integration of x is going to be x square by 2. This is going to be b square minus a square upon 2 times b minus a. Now b square minus a square can also be written as b minus a into b plus a. This gives us b plus a by 2. Now just by logic, if I say the probability of each value is equal, or probability density in this particular case, what would be the expected value, or what would be the mean of this particular distribution? It should be the middle value. Now the middle value is just going to be last value plus first value divided by 2. This gives us the mean of this distribution. Now to find variance, we'll have to find expected value of x square. We get getting b cube minus a cube by 3 times b minus a. Now b cube minus a cube can also be written as b minus a into b square plus 2a b square plus ab plus a square, not 2ab. So b cube minus a cube can be written as b minus a into b square plus ab plus a square. Now similarly, if I had b square plus a square, b cube plus a cube, that could have been written as b plus a into b square minus ab plus a square. We are not going to use this formula, but just for general reference, we should know these formulas. And this finally gives us b square plus ab plus a square by b minus a. Now let's find variance. Our variance of x will be e of x square minus e of x the whole square. So that becomes b square plus ab plus a square by 3 minus b plus a by 2 whole square. Or we can write this as b square plus ab plus a square by 3 minus b square plus 2ab plus a square by 4. Now simply cross multiply and solve this. You'll get 4 times b square minus 3 times b square, so we get b square. Then we'll have 4 times ab minus 6 times ab, so we get minus 2ab. And then we'll have 4 times a square minus 3 times a square, we get plus a square upon 12. This is nothing but b minus a whole square by 12. So this becomes our variance, b minus a whole square by 12. The next distribution that we are going to study is exponential distribution. For exponential distribution, we write our variable x follows exp and and we have one parameter, that is lambda. Lambda is same as Poisson distribution. It is some kind of rate per time. It can be per hour, per day, per week, per month, and we are going to see afterwards how we solve this particular sum. Now the fx, that is our probability density function for exponential distribution, is lambda e raised to minus lambda x. Now the limits for x is nothing but anywhere between 0 to t. So limits becomes 0, x greater than 0. Now here let's find our capital Fx. Capital Fx is nothing but from lowest limit to x1 integration of fx dx. The integration of e raised to x is nothing but e raised to x. So we get e raised to minus lambda x upon minus lambda. Is divided by the coefficient multiplied to x. So we get 0 to x1, and this will give us, when we put 0, we get e raised to 0. E raised to 0 is nothing but 1. When we put x1, we will get e raised to x1, and because we have a negative sign, we are going to get 1 minus e raised to minus lambda x1. So the lower limit becomes our first value. Because of the minus sign, minus minus will get us plus 1, and e raised to minus lambda x1, when we put x1, and because there is minus sign, we get minus e raised to minus lambda x1. So our generalized fx is nothing but 1 minus e raised to minus lambda x. Now this is one of the formula that we use a lot. So even though it is given in your formula table book, this is something that you should remember. While solving sums, we are going to use this a lot. Then next, let's find expected value. So expected value is nothing but integration for all values of x. So therefore 0 to infinity x into fx dx. Now whenever you have this kind of term where there is a function of x multiplied to another function of x, we need to use integration by parts. Now for integration by parts, we say if I am integrating two terms u and v, two functions with respect to x, then integration is going to be, first we take constant u and then we integrate v with respect to x, and then minus, we say integration differentiation of u with respect to x, and then integration of v dx, and this whole integration. So this is the formula that we call as integration by parts, and we can use integration by parts here. Now first of all, lambda is just a constant, it will come out. So our first function is x and the second function is e raised to minus lambda x. Now how do we define which of them is going to be u and which of them is going to be v? So basically there is a simple formula, we say liate. If you remember this word, it is going to tell you which one is going to be which. Now basically this liate, first is logarithmic values, then we have inverse, then we have algebraic, then we have trigonometric, and we have exponential. Now just because we do not have trigonometric or inverse, we can convert this into LAE. Now here, this particular, that means the values that are leftmost, that is logarithmic, will always be u, and this particular, that is rightmost values, will always be v. So exponential value will always be v and logarithmic value will always be u, and a depends on which one is which. So this particular term you can easily identify what is going to be your u and what is going to be your v. So here x is nothing but an algebraic formula and e raised to minus lambda x is nothing but exponential formula. So simply we have x as our u and e raised to minus lambda x as our v. I'll just take lambda common, and then first u is constant, so we get x, then integration of v, that is e raised to minus lambda x dx, then minus, we'll have integration, differentiation of u, integration of e raised to minus lambda x dx, and then dx. We'll have to integrate it again. Now, I always prefer not to write the limits when we are using this integration by parts. You can write the limits also. It just becomes too complicated or too congested while we are writing this particular formula. You can just, after solving everything, you can write the limits afterwards. So we get lambda x e raised to minus lambda x, integration will be e raised to minus lambda x upon minus lambda, and we'll have minus dx by dx will be 1. So we'll have integration here, we'll have e raised to minus lambda x upon minus lambda dx. So again we'll have to integrate this. We get lambda x e raised to minus lambda x on minus lambda minus, and another integration, again we'll get e raised to minus lambda x upon minus lambda, so we'll get minus lambda square. And now we'll put the limits 0 to infinity. So now first of all, this first term, when I put x is equals to 0, I am going to get 0. When I put e raised to minus lambda x, when I put x is equals to 0, I get 1. But what happens when we put infinity? Now, anything raised to infinity will be 0 if this particular a is less than 1, or let's say between 0 and 1. That means if a is a value that is between 0 and 1, then a raised to infinity becomes 0. Why? Simply, if I take a particular value 2, or you can say 1 by 2, a is nothing but 1 by 2. So the power, or a square, is going to be 1 by 4, a cube is going to be 1 by 8, a raised to 4 is going to be 1 by 16, and so on. So as the power increases, the value becomes smaller and smaller and smaller. Now simply, if the value, or if the power is infinite, such a large value that it is almost impossible to compute, then the actual is going to be so small that it is going to be almost equal to 0. Or in this particular scenario, or let's say in statistics that we are going to study, we are always going to study reachable infinity. Now there are two types of infinity in mathematics, where we say one infinity is unreachable and the other is reachable. Now in statistics we always use reachable infinity. So we are assuming this particular infinite value is reachable. So if we reach n is equals to infinity, then this a raised to n is going to reach equal to 0. So here when we put x is equals to infinity, e is a value. What is e? So it's an irrational value. So it is somewhere around 0.73. And when we have e raised to minus infinity, and nothing but a value that is between 0 and 1. So therefore we say e raised to minus infinity will be 0. So when I put e raised to minus infinity here, I am going to get a 0. When I put e raised to minus infinity here, I get a 0. When I put x is equals to 0 here, this particular term becomes 0. And when I put x is equals to 0 here, I get 1. So I get lambda minus, and then I'll have a negative for lower value. So I get a positive value, e raised to minus lambda 0 upon lambda square, or you can say this is going to be lambda upon lambda square, or 1 by lambda. So this becomes our expected value of exponential distribution, that is nothing but 1 by lambda. Let's find expected value of x square. So e of x square, nothing but integration x square fx dx for values between 0 to infinity x. So that is going to be nothing but integration 0 to infinity x square e raised to minus lambda x. I am taking lambda of our fx common, so I get lambda out dx. Again, we have integration by parts where u is going to be x square and v is going to be e raised to minus lambda x. So we get first x square common, e raised to minus lambda x. The integration for e raised to minus lambda x will be minus e raised to minus lambda x upon minus lambda, and then minus integration of differentiation of x square. I am going to get 2x then e raised to minus lambda x upon minus lambda dx. Now they are not expecting in examination for you to show every step of integration. So you can actually integrate it directly without showing this particular step. So we get lambda here. We are going to get 2 upon minus lambda outside, and we get integration of x e raised to minus lambda x dx. Now this is the term that we have already found out, so I can use this directly where this particular term. So I'll need more space, I'll write it here. We get lambda into, first of all, this particular term x square e raised to minus lambda x upon minus lambda, then minus 2 by minus lambda, and then integration of this is nothing but x e raised to minus lambda x upon minus lambda, minus we'll get e raised to minus lambda x upon minus lambda square. I've used this particular term directly from here. You can only use that in examination if you have found that in that same particular sum. So usually whenever you are finding e of x square, you have already found out e of x. So therefore it becomes easier. Now, let's put our limit 0 to infinity. Now simply, when we put limit 0 here, we are going, or let's say first infinity, e raised to minus infinity will be 0, then e raised to minus infinity 0, e raised to minus infinity 0. So all of these terms will be 0 when we put infinity as our value of x. Now when we put 0, this particular term is going to be 0 because we have x square multiplied. This particular term is also going to be 0 because we have x multiplied. But this particular term will be e raised to minus lambda 0, that is nothing but 1. So we are left with first lambda here, then only this term, but this will be multiplied. So I can say 2 by lambda and then we are left with minus e raised to minus lambda 0 upon minus lambda square. But just because this was the lower limit, this term is going to be negative and I get a positive value. And we get 2 by lambda square. So we get 2 by lambda square, that is nothing but expected value of x square. Let's find variance. Just do it here. So you'll get variance of x will be expected value of x square minus expected value of x the whole square, that will be 2 by lambda square minus 1 by lambda square, that is nothing but 1 by lambda square. So the variance of an exponential distribution is 1 by lambda square. Now let's find the median of an exponential distribution. Now what is the median of any distribution? Median is that point which divides our whole population in 50-50. That means one part or 50% of the population is less than that particular value and 50% of the population is more than that particular value. So if I want to find median, I'll just write that as m. Then I can say that probability x less than the median should be equal to 0.5. So the probability x less than m is nothing but capital Fm. Now we know the formula of capital F. Capital F is what? It is 1 minus e raised to minus lambda x. Here we are using m, so it will be lambda m. So this should be equal to 0.5. So that is nothing but e raised to minus lambda m is equals to 0.5. So m is going to be minus 1 by lambda ln of 0.5. ln is nothing but log to the base e. Use your calculator. ln 0.5 or m is going to be 0.693147 upon lambda. For a specific particular value of lambda, we can easily find what would be our median. Now, although you do not need to remember this particular term, but you should remember the procedure of which we are going to use median. Let's do a question here. Claim to a general insurance company's 24 hours call center occur at the rate of 3 per hour. What is the probability that the next call arrives after more than half hour? Now, how to recognize whether this particular question is of exponential distribution or not? Now, first of all, whenever you are going to see a question of a continuous distribution, except for exponential distribution, every distribution will be specified and it will say that this particular term is following this kind of distribution. Now for exponential distribution, you will always find a rate in the question. Now if you see in this question, they say call center occur at the rate of 3 per hour. So there are 3 calls per hour. So our lambda becomes 3 per hour. So whenever you have rate, now you will have rate in 2 questions. Either it can be a Poisson distribution question or it can be an exponential distribution question. How would you recognize whether it is Poisson or an exponential distribution? Simply, a Poisson distribution or our variable when we use Poisson distribution has to be a discrete variable, and when we are using exponential distribution, it has to be a continuous variable. Now simply the time, they are saying next call arrives more than half hour. So we are actually finding the time between 2 calls. Time will be a continuous distribution. So you can say our variable x, or you can use t for time, will follow exponential distribution with lambda equal to 3. Now we need what is the probability that the next call arrives after more than half an hour. So we need probability x is greater than half hour. Now the rate was per hour. So therefore my units of x are going to be in hours. So therefore half, or you can just write 0.5. So probability x greater than 0.5, I can write it as 1 minus probability x less than 0.5. That is nothing but 1 minus capital F 0.5. Capital F is nothing but 1 minus e raised to minus lambda 0.5, and that is going to give us e raised to minus lambda 0.5. Lambda is 3, you can substitute here or you can substitute it directly in your answer. Now how to get to e raised to? Simply press shift and then ln button. So that is e raised to. All the yellow buttons or all the things that are written in yellow can be accessible after pressing shift, and all the red things written can be accessible after pressing alpha in our calculator. So e raised to minus 3 into 0.5 is going to give us 0.22313. Now in your examination they expect answer to be 3 decimal points, but I suggest write at least 4 decimal points. It just saves you time by not rounding it off. You can just simply write this as 3.1 even if we had some value, let's say 3.7. So it takes time for us to think. It might be a split second, but it still takes time for us to think whether we have to round it up or round it down. So if you write that particular 4th digit, it does not matter whether you are rounding it up or rounding it down, because the actual answer expected is of only 3 decimal points. And whenever possible, write it in fractions. These answers cannot be written in fractions, so no problem, write it in decimal. But if possible, write it in fractions, and then always lowest possible fraction, and then also write it in decimal points. Let's move on to gamma distribution. Now before we study gamma distribution, we need some knowledge about gamma functions. Now gamma functions is given in your table formula book also, that will be provided to you in your examination, and it is on page number 5. So gamma function is written as this particular sign is called gamma and then alpha. So this is gamma alpha is nothing but integration from 0 to infinity of t raised to alpha minus 1 e raised to minus t dt, where our alpha is going to be always greater than 0. Now this particular gamma function was derived from the factorial function. Now the problem with factorial function, like we write it as n factorial. N factorial is nothing but multiplication of n into n minus 1 into n minus 2 till last we'll get 1, till we go up till 1. So you can say it is nothing but multiplication of all natural numbers up till this value n. Now the limitation of this factorial function was that n can only be a positive integer. Now what happens if I need to find values that are not integers? Now first of all, gamma function, gamma will always be positive also. But what happens if I need a non-integer value? So basically what they did was, some mathematicians, they plotted all the values of this particular function. So let's say for 0 we'll have 1, for 1 we'll also have 1, for 2 factorial what I am doing is on x-axis I'll have x, and here I have x factorial. So for 3 we'll have 6, let's say, for 2 we'll have 2, for 3 we'll have 6, 4 we'll have 24, let's say somewhere here, and then 5, we'll have 120 somewhere here, and so on. So basically they drew the graph and then they connected the lines and then they made this particular line into a function. So what I can do is I can just, if I want to find, let's say 2.5 is going to be somewhere here, all I have to do is just plot the line and then find the particular value. So the problem is carrying this graph, and whenever we are trying to use a graph, it will have some kind of error. So we made it into a particular function. This was this gamma function. Now this gamma function has some properties that are very similar to factorials. We are going to see that. First of all, gamma of a particular value alpha is nothing but alpha minus 1 into gamma of alpha minus 1. Now factorial has, what is the property of factorial? N factorial is equals to n into n minus 1 factorial. So it is slightly different from factorial, but it uses similar kind of property. It's not the same, so don't confuse them. So gamma of alpha is alpha minus 1 into gamma of alpha minus 1, and we have gamma of alpha equal to alpha minus 1 factorial if alpha is integer. And one of the limits, I'll have gamma of half as root pi. So pi is our normal value, 3.14. So gamma of half is nothing but root of pi. These are some properties that we are going to use in either finding gamma distribution or also afterwards finding particular value. Sometimes they do ask you a question. I have seen a particular question where we needed to use this gamma of pi, root 2 pi. Okay. So basically, let's say if I have, or if I need to find gamma of 1.5, gamma of 1.5 is going to be nothing but half of gamma of half. Gamma of 1.5 is nothing but half of gamma of half, is basically alpha minus 1 into gamma of alpha minus 1, and gamma of half is nothing but half to root pi. So we can use this method to find different values of half values of gamma. For integers we can use, or we can convert into factorial, but for half values we can use gamma of half to find particular values. Now let's move on to gamma distribution. Now gamma distribution was derived from gamma function, but we are not going to go into specific how it was derived. We are going to understand that afterwards. Now gamma distribution, we say x follows gamma. You can just write GA or you can write the whole gamma with two parameters, alpha comma lambda. So we have two parameters here, alpha and lambda. Lambda is again some kind of rate per time, and alpha is just a constant that we use to change these particular values. Now here our fx, probability density function of gamma distribution, is nothing but lambda raised to alpha x raised to alpha minus 1 upon gamma of alpha e raised to minus lambda x. The limits are nothing but 0 to infinity, so we can write x is greater than 0. So the possible values that our gamma distribution variable can take is nothing but 0 to infinity. Now unfortunately we cannot find capital Fx for this particular term. Why? Because we have x raised to alpha minus 1 and e raised to minus lambda x. So basically we have two functions. Now we used integration by parts to find two functions, but if you see when we had integration of x square e raised to minus lambda x, where we had algebraic value and we had a square value x square. So we needed to do integration by part twice. So whenever you have x cube, you'll have to do integration by parts 3 times. And whenever you have x raised to 4, you'll have to do it 4 times and so on. But what happens if we do not know the value of that power? So it becomes impossible to do integration by parts and find that particular value. So therefore we cannot integrate this fx to find our capital Fx or probability x is equals to less than a particular value of x if we do not know this value of alpha, or even if this alpha is not an integer. So we do not know how to actually integrate these particular values where this particular value is not an integer. So therefore in questions you will find alpha to be integer, and it is usually 2 or 3 because it becomes easier to use integration by parts. So anyways, we cannot find capital Fx. Let's move on to expected value. Expected value will have integration 0 to infinity x into fx dx. Now I just said that we cannot integrate this fx. So I am using integration here. So basically for this integration we are going to use the gamma function. Now how? We'll see that. So we have integration from 0 to infinity x into fx dx. That is going to be nothing but integration 0 to infinity, and then I'll multiply this x into this, and I'm going to get lambda raised to alpha by gamma alpha x raised to alpha e raised to minus lambda x. So I got x raised to alpha because I have multiplied x raised to alpha minus 1 into this particular x. Now here what I can do is I can take lambda x as a dummy variable, or you can say another variable t. So lambda x is equals to t. Now if I take lambda x as t, then lambda dx becomes my dt. Here I need dx. So lambda dx becomes my dt, or you can say I'll get integration 0 to infinity, because when I put x is equals to 0, t is also 0, x is equals to infinity, t is also infinity. So we get, first of all, here t raised to alpha by alpha factorial gamma alpha e raised to minus t, and then I'll get dt by lambda. So dx is nothing but dt by lambda. So if I remove 1 by lambda out, integration 0 to infinity t raised to alpha by gamma alpha e raised to minus t, or I can take gamma alpha also out. I'll just take gamma alpha outside, dt. So basically we have this particular value. Now does that look very similar to a function that we have derived? Just the difference is here we had minus t raised to alpha minus 1, and here we have t raised to alpha. So if I replace this alpha with alpha plus 1, I'll have to replace this alpha with also alpha plus 1, and alpha plus 1 minus 1 gives me alpha. So basically gamma of alpha plus 1 is going to be nothing but 0 to infinity t raised to alpha e raised to minus t. So this particular term is nothing but gamma of alpha plus 1. Then property of gamma, I can use that here, and gamma of alpha plus 1 can be written as alpha into gamma of alpha, and gamma of alpha upon gamma of alpha will be 1. So we get alpha by lambda. So this becomes our expected value, that is nothing but alpha by lambda. Why could we not integrate this fx for finding capital Fx, and still we integrated e raised to expected value of x? For that, these limits is very much important. When we were finding capital Fx, we used from the lowest value to a particular value x1. So here we need 0 to infinity. To make it into a gamma function, limits to be from 0 to infinity. Let's find expected value of x square. So here we are getting lambda raised to x upon gamma of alpha x raised to alpha plus 1 e raised to minus lambda x dx, right? So basically now all the difference between this term and this term is just we have one extra x. Here again we are going to use the same concept. We'll use lambda x as t, and we need dt, so lambda dx becomes our dt. So to make lambda x as t, I need alpha plus 1 lambdas, so I can say this is going to be t raised to alpha plus 1 upon lambda, and we'll get e raised to minus t. So here I can take lambda square gamma alpha common, dt. Again it is similar to the gamma function. Just the difference is here we had alpha plus 1, here we have alpha plus 1. So for gamma of alpha we get alpha minus 1. So to get alpha plus 1, it is going to be gamma 2. Again we can use this particular property to expand this particular gamma alpha plus 2. It will be gamma of alpha upon, or you can say alpha into alpha plus 1 by lambda square. Now I'll explain this again. Gamma of alpha plus 2. Now gamma of alpha plus 2 will be nothing but alpha plus 1 into gamma of alpha plus 1. Then gamma of alpha plus 1 can also be written as alpha into gamma of alpha. So therefore we get gamma of alpha plus 2 same as alpha plus 1 into gamma alpha into gamma of alpha. Let's do variance here. So variance we are getting variance as alpha by lambda square. A gamma distribution can fit many different distributions. Now basically, a gamma distribution, when we change different values of alpha, we can actually change the height of that particular distribution, and when we change different values of lambda, we can change the width of that particular distribution. So we can basically fit that particular distribution to many different distributions. The actual shape or a general shape of a gamma distribution looks something like this. It is going to start at 0, and the probability at 0 will be 0, and then it has some peak, and then it goes up till infinity. So this, when we change the value of alpha, we can change the height, and when we change the value of lambda, we can change the width, and therefore we can fit this particular distribution, gamma distribution, to many different kinds of distributions. Now the disadvantage of gamma distribution is that it is very difficult to actually calculate different terms. If I need to find probability, I cannot integrate this particular fx unless and until I know a particular value of alpha. And if alpha is very large, let's say it is 10, 20, 30, I'll have to integrate it that many different number of times. And if it is a non-integer value, then it becomes more difficult to find. So basically, gamma distribution, even though it can fit many distribution, is not very widely used just because of this particular problem. We cannot find probabilities. So what we do is we basically make it into tables. Now unfortunately, when we make tables, the problem with distributions where we have two parameters is that we have to change different values of alpha, and we'll have to change different values of lambda, and also we'll have to find that for different values of x. So basically we have three things that are varying. So whenever we are making tables, it becomes very difficult if we have three things that are varying. So basically what we did was we changed this gamma distribution to another distribution that is nothing but chi-square distribution, and we change it in such way that it turns into one single parameter. We are going to see that when we study chi-square distribution next. So for chi-square distribution, we have x follows. Now there is a special symbol for chi-square. It looks like x, but it is a squiggly kind of x. This is a special kind of x, and then we write square. So this becomes the symbol for chi-square. So we have x follows chi-square, and then we have the parameter nu. It's the special kind of v. So basically, while writing chi-square, you can write it like this, and then this becomes our nu. Now basically nu is nothing but degrees of freedom. Now we'll understand what is exactly degrees of freedom in later chapters. Right now, it's just degrees of freedom. Now chi-square can be used in itself, but it is mostly used to convert gamma distributions into chi-square distributions to find different probabilities, because now here we have only one single parameter. Now any distribution, any gamma distribution can be converted into chi-square distribution perfectly. There is no approximation. So basically every gamma distribution can be converted into chi-square distribution, and the probabilities is going to stay same. Now how do we convert gamma distribution into chi-square distribution? So if I have, let's say, x follows gamma distribution with alpha comma lambda. These are my parameters of gamma distribution. So 2 lambda x, my new variable 2 lambda x, or let's say y, is equals to 2 lambda x, will follow chi-square distribution with 2 alpha. So we have y is equals to 2 lambda x will follow chi-square distribution with 2 alpha as its parameters. We can use this procedure to find every gamma distribution probabilities. Let's take an example. If let's say I have x follows gamma distribution with alpha as 2 and lambda as 1.5, and we need to find probability x, let's say, less than 4. We need to find probability x less than 4. Now what we can do is, we can convert this gamma distribution into chi-square distribution. So always first write x follows gamma distribution 2, 1.5, and then you can write 2 lambda x follows chi-square distribution. Now preferably your x should look a little bit different from your chi-square. So try to make it a little bit different, chi-square, and we'll have 2 alpha, alpha is 2, so we get 2 into 2, or you can directly write 4. So this becomes 2 lambda is nothing but 3, so 3x will follow chi-square 4. Now while solving, we write probability x less than 4 will be equal to, I can write probability 3x less than 12. All I did was multiply 3 on both sides. Now 3x is nothing but chi-square with the parameter 4. So I can say this is nothing but probability chi-square 4 less than 12. Now how to find probabilities of chi-square? Come to our table formula book, page number 164 and page number 165, we have chi-square tables. Now how do we read chi-square tables? Whenever we are reading a particular table, always see the graph that is given in the top. Now the graph shows us the shaded region between 0 to x. That means we are actually finding probability less than that particular value x. So if you see, they have written nu, their parameter nu, and they have given us different values of nu and different values of x. Nu 4 is on the next page, that is 165. Just see nu 4 and use that column to find probability less than this particular value x. So we need probability less than 12. So we have 0.9826. So this is nothing but 0.9826. Probability x less than 4 is same as probability chi-square 4 less than 12. And that is nothing but 0.9826 from our tables. Now basic distributions are very similar to each other. Actually, exponential distribution is nothing but a special kind of gamma distribution, and chi-square is also a special kind of gamma distribution. So if I say I have a gamma distribution where alpha is equals to 1, then that is same as exponential distribution with parameter lambda. So gamma distribution with alpha 1 gives us the exponential distribution with lambda. You can check that by putting alpha is equals to 1 in your probability density function. You'll get a probability density function of exponential distribution, and also you can check the expected value and the variance, and you will find them to be same. And we also say that a gamma function with nu by 2 comma 1 by 2 lambda equals, and nu by 2 will follow chi-square distribution nu. So again, chi-square is nothing but a special kind of gamma distribution. And how do we convert it? If we say I have an particular variable x that follows gamma distribution alpha comma lambda, then 2 lambda x follows chi-square 2 alpha. Simply, this is how we convert every gamma distribution into chi-square distribution. Let's move on to beta distribution. Now, before we study beta distribution, we are going to study beta function. Now, beta function is related to gamma function, and gamma, basically we have two different values. A beta of alpha comma beta will be nothing but gamma of alpha, gamma beta, gamma of alpha plus beta. And integration terms, this is how we write it, that is integration 0 to 1 x raised to alpha minus 1 and 1 minus x raised to beta minus 1 dx. Now the x variable here and the t variable that we studied in gamma function, those variables are called as dummy variables. Now basically all those values are going to be put before we actually find the values of alpha and beta. So this x and t will not affect the actual value of the beta function or the gamma function in the previous gamma function equation. So they are called as dummy variable. They have no effect on the actual values of the function. Now for beta distribution, we write it as x follows beta with parameters as alpha comma beta. So these are the two parameters of a beta distribution. Now beta distribution is such kind of a distribution that we can make it fit into any kind of graphs. So it can go from a straight line into any kind of curves by changing the values of alpha and beta. Now that is why the beta distribution was actually formed, because it can fit any kind of distribution. So basically it was derived from this beta function. Now we'll see how do we derive that. Our fx is nothing but gamma of alpha plus beta upon gamma of alpha gamma of beta into x raised to alpha minus 1 1 minus x raised to beta minus 1, where our values of x is between 0 and 1. If you see the similarities between these two particular terms, you can see basically we use the dummy variable as our distribution variable here. So we did the same thing in gamma distribution, but it was not that clear that time. But here it is very clear that we are using our dummy variable as our actual variable in here. So the limits of our variable becomes between 0 and 1. So we can actually fit this distribution into any kind of distribution, but the values of our x are going to be always between 0 and 1. So you can actually find proportional values using this particular distribution. Now the problem of finding capital Fx is the same as gamma distribution, just because the integration of this particular term becomes very difficult. So let's then integrate it in expected value. So expected value of x will just be integration of x fx dx for the values between 0 to 1. So now here I can write this as 1 by beta of alpha comma beta, just beta function, integration 0 to 1, I'll have x raised to alpha into 1 minus x raised to beta minus 1 dx. Now again, this is very similar to our beta function, the integration form of our beta function, and integration form here are very similar. So the difference again, here we had alpha minus 1, here we have alpha. So what we do is same thing. If I put instead of alpha, if I put alpha plus 1, I'll get here alpha. So this is nothing but beta of alpha plus 1 comma beta. Now beta of alpha plus 1 comma beta will be gamma of alpha plus 1 gamma of beta upon gamma of alpha plus 1 plus beta, or I can write it as alpha plus beta plus 1, then upon we'll have gamma of alpha gamma of beta upon gamma of alpha plus beta. Gamma of beta will cancel out, and gamma of alpha plus 1 can be written as alpha into gamma of alpha, and gamma of alpha plus beta plus 1 can be written as alpha plus beta into gamma of alpha plus beta. So we'll have expected value as alpha upon alpha plus beta. This becomes our expected value. Let's find E of x square. E of x square will have integration 0 to 1 x square fx dx. That will give us again, this term can be written as beta of alpha plus 1 comma alpha plus 2, not alpha plus 1 comma beta. So this gives us gamma of alpha plus 2 gamma of beta upon gamma of alpha plus beta plus 2 upon so again we can write alpha plus 2 as alpha plus 1 into alpha into gamma alpha upon we can write alpha plus beta plus 1 we get alpha plus 1 into alpha plus beta plus 1 alpha plus beta. Let's find our variance. Expected value of x square was alpha square plus alpha upon alpha plus beta plus 1 into alpha plus beta, and we'll get minus, here we have alpha by alpha plus beta whole square. So I can take alpha upon alpha plus beta as common, cross multiply and solve it. You will find final answer for variance. Variance of x is nothing but alpha beta upon alpha plus beta whole square into alpha plus beta plus 1. Now you don't have to actually remember any of the expected value and the variance because they are all given in your table formula book. So you can use it directly from the book, but I suggest values for exponential distribution and gamma distribution are very widely used. So therefore we should not waste time in just searching throughout the book. So just remember those values.